So we'll now look at an example schematic that you can use in constructing a BLDC motor control. Basically, in a typical scenario, you have the 6 MOSFET bridge and some sort of a current sensor. So you can have either the current sensor on the positive side, or you can have sometimes people have it in the ground as well, so we call this the ground. There are advantages in having the current sensor on the positive rail. I'll explain that in a moment, but let's draw the 6 MOSFET bridges. So you have one MOSFET there, another here, of course you have the diodes across the MOSFETs. They are built in, so they just go without mention. These diodes, they're basically freewheeling diodes. Okay, so your 3 motor phases basically get connected here. One, let's call it A, another one, let's call it B, and there's your third phase, C phase. To drive the motor, you may want to use the same type of MOSFETs. Sometimes people use different ones, so for instance they can use the P-type on the upper side and N-type on the lower side, but it's better to keep it all symmetrical and keep them all N-type. But of course when you have N-type on the higher side, then you actually need a special driver to turn these MOSFETs on because of the voltage jump from here to there. You've got to consider that. You can use these drivers are called high side, low side driver. I've personally used the 40 amp MOSFETs IRZ44N, I believe it was, and the high side low side drivers of IRS2011S. Basically, a couple of things to consider with the high side low side drivers. They're SOIC packages. You have 8 pins coming out of them, 2 of which is used your high side output and the low side output, and if you have the high side in and a low side in, and these inputs are coming from your microcontroller, so they're the logic inputs. From micro. These outputs, the high side and low side outputs, they're basically going directly onto these inputs for the gates of these MOSFETs. You're better off putting a series resistor before you hook this up to the MOSFET. This resistor has the effect of limiting the current, so it won't blow the gates off if there's a high enough current. So normally we tend to use 10 ohm resistor, but of course you can look up the data sheet to work out how much current, well, how much charge you need to turn the MOSFET on, and work out your resistance accordingly. It's often advisable to have a diode across the resistor as well with this polarity, and the reason for this diode is when you turn the MOSFET off. So let's say we had this one, hooked up to here. So when you're turning the MOSFET on, it's all fine and dandy. So you have electrical charge going through there, and it's turning it on. But when you're turning it off, you really want to turn the MOSFET off as soon as you can. And to do that, that's when you're using this diode. So the charge that's in the gate, it flows through the diode and it gets shorted out to the ground, because your low side is being brought down by the microcontroller, and as it is being brought down to the ground, the charge flows out of the diode and into the ground, and hence it turns the MOSFET off much quicker than if you just had a resistor, because then your MOSFET gate is really a capacitance gate, and your RC will mean that it's discharging very slowly. So by having a diode there, you're discharging it much quicker than you would normally. A couple of things to mention regarding this circuit. So it's really useful to have some sort of filter caps. So you want to have a reasonably big one, say a couple of thousand microfarad, and of course a couple of small ones too. So the 0.1 microfarads. You may want to have them very close to the MOSFETs, and real good design, like a controller that's been well designed, will also have some sort of snubber across the MOSFETs. I don't want to discuss the snubber circuits. That's beyond the scope of this video. If you're interested, you can Google them and come up with a lot of reading materials. But for typical RC application, I would say you don't really need to consider them. With the filter capacitors, you would also want to have filter capacitors across the supply to these high side, low side drivers. The other thing is the purpose of having these high side, low side drivers is to really turn the high side MOSFET on, and to do that they use a charge pump capacitor. So if you look at the data sheet for IRS 2011, you'll find that they have a charge pump capacitor up here, and normally you can have somewhere between 0.1 microfarad to 1 microfarad. It really depends on how fast you're switching the high side or the low side. If you're switching reasonably fast, you can go on to the lower scale, so you can have lower microfarad capacitance. If you're doing it slow, then or your pulses are longer, then you need to have a higher capacitance as your charge pump. And depending on what your charge pump capacitance value is, you ideally want to have at least 10 times that as your filter capacitor across. So if this was your positive, then you want to have your filter capacitor 10 times. Let's say your charge pump was 1 microfarad, and then you want to have it, your filter cap as 10 microfarad to your ground. Then now let's talk about the current sensor. With the current sensor, in my designs, I originally had a resistor in series with the ground, but that has potential. Well, basically the idea is you put a resistor in series and you look at the voltage drop across the resistor to work out essentially the current flowing through the resistor. There are some potential disadvantages in doing that. I then found a good solution with provided by Allegro Microsystem. They are providing current sensor chips where you basically pass the current, you consider it as if it was a resistor, and they provide analog outputs from the module. So it's a module no bigger than about this size, depending on your current requirement. a module of that size will give you up to about 200 amp. If you check out their website, you will find that they have these devices. I have used ACS 758. That is the and I've used the 50 amp device, but of course the 100 amp and 200 amp also comes in the same module, a similar size module. So what you get out of this chip is 3 other pins, and one of them is your ground, and that's your positive, let's say, and the third one is your analog value. So and that's proportional to the supply and the current that's passing through. So it's a ratiometric output. This output here, you ideally want to voltage divided. So depending on, let's call this one your D. So if this was your D, to voltage divide that to ground with a filter cap. Never forget these filter caps. They're very useful. Now the reason you want to voltage divide them is because depending on the microcontroller you're using, your ADC input to the microcontroller may be low. So for instance, if you're supplying this ACS 758 with a 5 volt, then you could potentially have on your output, if you go onto the full scale, you could potentially have up to 5 volt on your output D. So if your microcontroller ADC did not have a 5 volt capable input, then you want to have a voltage division made, and simple R1, R2 resistor divider network will give you the adjusted voltage level that you desire. So in my case, I had used the Xmega 168. My apology, in my case, in my later design, I have used Xmega 32U, sorry, AU. And these tend to have maximum ADC level tolerance of 2.7 volt. It's unfortunately they don't, even though the chip microcontroller operates up to 3.3 volt, it doesn't go, the ADC does not accept up to 3.3 volt. It's actually 0.6 volt, less than that. So it's 2.6 is the maximum you can use for the ADC level. So you have to make sure you use a reasonable voltage division here in order to obtain the level that the microcontroller can handle. There's a few other voltage divider networks you have to consider. For instance, when you are doing back EMF sensing, as discussed previously, you need to look at the back EMF on these phases. As you fire 2 phase, you want to look at the third one and keep monitoring it. As it crosses 0, that's when you know that you're ready to fire the the following pulse to the other 2 phases. So to look at these back EMF values, you could be potentially reading up to the supply rail. So for example, if you were supplying this with 12 volt supply, you could potentially be getting up to 12 volt being read across here to ground. So you want to create a voltage divider network for back EMF reading. So if we look at just the phase A itself, you will have a resistor off to the ground and a capacitor filter. A few words of advice: you want to have these resistors less than 10k, and that'll give you noise improvement. For the capacitor, you don't want to have the capacitance too big. You also want to have something like 101. That's what I've used, which is 0.0001 microfarad. The problem is if you have any bigger than that, then the decay would be too quick. So, for example, your pulse, if you look at the pulse that you will see on phase A, it will be something like that. Oops. It will die down depending on your duty cycle of your PWM. So if your duty cycle is that wide, then and if you had a bigger capacitor, it will be something like that, and you don't want that. You want the pulse to show up as quick as possible without the least amount of decay, and the level you want to see on the pulse is somewhere like the maximum level you want to see is somewhere around 2.7 volt. So just keep those words in mind. So you want to use less than 10k as your resistor, and your capacitance to be reasonably small, but at the same time giving you filtering capability. In my situation, I used a resistor of 6.8k and 1.8k. That gives you the desired ratio between a maximum of 12 volt there and a maximum of 2.7ish volt up to there, and that's adequate for your microcontroller. So far you've got a current sensing analog input to going to your microcontroller, and 3 other analog measurements. You have the for each of the phases. So you have the ABC 3-phase. The other last one that you would like to have is the voltage reference. So what we are really trying to do is, with the phase readings, we are trying to find the zero crossing for each of the phases. So as you're firing 2 of the phases, you're looking at the back EMF on the 3rd one, and the characteristic for the back EMF is that it goes from, depending on the rotation and the commutation steps, it goes from maximum to a minimum, and this is what you are looking at. So your zero crossing is really in between the 2 states, and so if you apply the motor volts, which could be here or there, ideally there won't be any voltage drop there if you assume that the resistance for this module is very small. If you apply the motor, if you look at the motor volt and use that to be your ADC Vref, if you set that to be your motor volts, volts maximum 12, let's say, then to detect a halfway value range at the phase level, these are your ADC inputs, other ADC inputs. To detect a halfway, you're really looking at a value of 1024 as your ADC raw value. If with the at Xmega 32 AU, you can, the full scale raw value is 2048. So to detect a halfway, you need to look at 1024 nearabouts. You'll probably find after constructing that you will have to tweak this halfway value. Often it's more like 1020 or 1030. So that value, to make the motor run smoother, you may need to adjust that value. So if you set the Vref to your maximum, then that means any measurements, any halfway measurements will show up as 1024 when you do the raw reading. Now this creates other problem then, because if you do that, then you don't really know exactly, in terms of analog values, what the value of these inputs are. So to do that, you basically want to introduce another known voltage source on a fourth analog input, let's call it E. You could choose something like a 2.048 voltage reference, constant voltage reference. There are I think from memory it's LM4040, and there are different versions of them, so I have used the 2.048 volt version. Basically what you want to do there is they're wired up like this, and again, don't forget the filter capacitor. So this would be your motor volts. I'm sorry, this would be your 3.3 volts, and typically 2.2k resistor, and over here you're expecting 2.048 volts. And so if you connect a network like this to one of the ADC sources, what that will do is you can back calculate your original ADC VREF level in terms of analog values. So rather than having it in terms of raw 2004-8 level, you actually get an analog level for that. You do that by considering this. So let's say your ADC level gives you a raw value of 0 to 2047, and that is your full scale. Actual analog value, you're expecting that to be up to 2.7 volts. So if you have your voltage reference to 2.048, which is the real analog value, you would be expecting a raw value less than that to represent 2.048. So your actual 2.048 would be somewhere up here, 2.048, and that will give you a raw value reading less than 2.47. So you can use this to come up with a measurement for your motor volts, which we assumed at the beginning is somewhere around 2.7 volts, but of course it doesn't have to be. What is really constant is the actual 2.048 volts that you get out of the voltage reference, which will correspond to a given raw value when you're measuring with the inbuilt ADC. Now, once you know an analog representation from 0 to X raw value, you can easily calculate or back calculate the full scale value that you would that you would expect to see at that raw value level 2047. You can then use the same scale to calculate the shunt current level. So if you were feeding the shunt current level, which is your D, or D voltage division divided, which is your dV, then you could use the same ratio that you obtain here to get an analog reading value for your current output. Okay, so that's the ADC part of this video, the ADC measurement part of this video. We'll now look at the logic outputs. So you have 6 logic outputs that are going into 3 pairs of high side, low side drivers. So you have each going for 1, 2, 3. Therefore you have the 6 logic outputs coming out of the microcontroller. We'll call these as follows. So let's say if this is your micro, we will have the A low, A high, B low, B high, C low, and C high. To drive a BLDC motor in sensorless mode, you have to make sure you drive the high sides with PWM. So this is the high side. You have to make sure that you have PWM on the high sides only, and only high sides. Now I have used at Xmega 32 AU. Now this has an interesting feature called AWEX, Advanced Waveform Extension module, which is essentially designed to drive 3-phase or even 4-phase motors like this. If you use that, then you can use the built-in PWM generator as well, so you can pipe the PWM waveform through the high side. If you don't use the at Xmega 32 AU, let's say you used a at Mega 16 or something, then you could use any of the 6 IOs and just have the top side, well again the high side MOSFETs being driven by the PWM, and you can use a quad AND gate package and just use the 3 AND gates in it. So for example, if you had let's say 3 AND gate out of a quad package, you could wire them as such. You could have the second from each being connected. Oops. And that one. So you could have phase A, logic A, sorry, AH, BH and CH being hooked up there, and the third common one is your PWM. So what this will do is, no matter when the pulses are coming into these inputs, the PWM will make sure the pulses come out on the output as a PWM version of that waveform. So for example, if you had a waveform like that, over here you will get a waveform like that. So the width over here will be the same width over here. So you can use this sort of topology using AND gate as well. So that's pretty much it in terms of the schematic design. You may want to have things like 12 volt to 3.3 volt DC to DC converter. That it'd be to power your microcontroller. Or to do any other things that you want to do in your circuit board to power them. Don't forget, of course, the diode clamps. They're very important, and I've learned it the hard way. I've had a situation where one of the phases came off the motor, and that back EMF was so high that it actually destroyed, even though I had the voltage divider network and then passing it on to the ADC, the voltage must have been really high to actually kill the ADC input for the microcontroller, and this happened. So by having a diode clamp, which is basically, if you look at the actually going back to this level here, which is the bit that goes into your microcontroller, the ADC part of your microcontroller, you want to have a diode clamp for each of the ADC inputs. So let's say for this phase you want to have a diode as such. This goes to ground, and another diode here which goes to your VCC. Now this VCC could be would have to be the supply of your microcontroller. So what this diode clamp does is, if this rail goes any higher than 3.3, then it will bring it down to ground, and if this goes any lower than the ground, it will bring it up to ground. Well, it will short it out to the ground. So that way you're pretty much guaranteed that you cannot, this input cannot be any lower than the ground. Well, it can be. It depends on the voltage drop across the diode. So generally, if you use 1N4148, which is probably not suitable because you can have potentially large currents, so you want to use a bit more heavy-duty diode, but perhaps a faster one. But typically they have 500 millivolt voltage drop. So what that means is you could go below ground level by 500 millivolt, and you could go above 3.3 volts by 500 millivolt. I'm afraid that's as best as you can do if you with such a simple protection, and I don't think such a level will kill the ADC input for the microcontroller.